Let's take a look, chapter number 8. In this chapter, we are trying to understand the concept of gravitational potential energy first. Then we will include that into our previous chapter concept, which means the work done energy theorem. Then we will modify work done energy theorem to a new aspect by including work done due to non-conservative forces, which means we're going to study the forces in terms of two categories, conservative type forces and non-conservative type forces. And then at the end, we will take a look a little bit of deeper into this concept of work done in terms of potential functions and how the calculus is actually important to understand the work done potential energy concept in general, okay, in more mathematical model. That's the plan. So let us start first with the concept of potential energy gravitational. So in this case, we'll consider I have object right here. Let's consider I have mass m object at point A, and then we'll lift the object upward direction by applying a force Fa. Then if you look at the free body diagram, force Fg downward direction, I'm moving the object upward direction with constant velocity, which means y-axis acceleration 0. I'm going to lift it from point A to point B. At point B, total displacement travel going to be h, okay? Then eventually object going to be right here at point B. And then during the motion, let's calculate the work done for each force. Let's consider work done due to applied force. That should be applied force, the dot product, the delta y travel. So the magnitude of applied force, magnitude of delta y is positive h, upward direction, and the angle between them is 0. This will become just Fa times h. Now, if you apply sum of all the forces along y-axis during the motion is equal mass times acceleration along y, the forces upward direction applied force, negative direction force of gravity equals 0. Applied force technically equal force of gravity. Force of gravity we know mg, right? So which means the work done due to applied force is just force of gravity times ch, which is positive mgh. Let's calculate work done due to force of gravity. Then the force of gravity vector dot product the delta y vector. Force of gravity vector magnitude delta y magnitude is h, angle between them 180. So the cosine 180 is negative 1. It's going to be negative fgh. That going to becomes negative fgh. What does that mean? So which mean if I want to lift the object against the gravity, I have to add the energy into the system. That negative sign actually means that. Okay. Now let's define the concept of potential energy gravity. I'm going to use the letter U for the potential energy. G, small g means the gravitational potential energy, which we define as the negative the work done due to gravitational force. Why we define that way? After I lift the object upward at point B, if I create or if I make my applied force equal to 0, object start falling down automatically. Object can go back against to the ground level. Ground level we define as a potential energy 0 point. So which means the at point B object has a certain amount of energy. That energy can bring the object backward to the ground level. So that's why the potential energy at point B or any point above the ground level is positive mgh. Okay, that's the idea. Or force of gravity times the height h above. Now, the another aspect of this potential energy gravity is the gravitational potential energy can be positive or negative, which means if you go above the ground level, you're moving to the positive y-axis direction. So we're creating positive potential energy. And if you move downward direction relative to the ground level, you move in negative y direction, you're going to creating negative potential energy. That's the idea. Any object above the ground can come back to the ground level automatically because it has stored energy. But if any object below the ground level cannot come back automatically, we have to bring that object by applying external energy. That's the idea of negative energy there. Okay. Now, similarly, if you take a look, if I bring this object back to the ground level, bring it out by applying a force and then bring it back against the towards the gravitational force. If I calculate net work done over closed surface, the closed loop, which means work done from A to B, and then work done by B to A under gravitational force, work done from A to B gonna be negative the FGH. Work done from B to A gonna be positive the FGH. So the total work done becomes zero, which means if I move the object against or towards the gravity along the closed path, which means I have to come back to the starting point as it is. So then my total work done becomes zero. What does that mean? These kind of energies are conserved. That's the idea. Or another way, what we call this force, F of G, is actually conservative type force. Okay, that's what we're trying to understand. Next, can we categorize all the type of mechanical forces into two basic categories? One type of force called the conservative type force, which means it's not going to change the energy from mechanical to any other type. It can store energy and then release energy, like the potential energy. And then there's other type of forces which doesn't store energy, which actually destroy the energy from the system, such as friction force always can convert mechanical energy into a thermal energy. Okay, so that's our next plan. Let's take a look the basic idea of this potential energy concept first. So the potential energy is actually due to a conservative type forces, right? So which means if I have a force, if I calculate the work done due to this force over closed path, okay, work done, I'm gonna write if dr can be x or y, okay, delta r, that can be x or y. So that is a small work done, and then if I integrate that, I'm gonna get the full work done. Then if I do the work done along closed loop, that closed loop, I'm gonna put that circle into the integral, which means the closed path, okay. Closed path means you come back to the starting point like we did earlier. So the W due to force of gravity from A to B plus W due to force of gravity from B to A, then I back to the starting point, that should be zero. There's no any energy lost during that path. Whatever we stored goes away, that's it, right? So that kind of forces is actually called the conservative type forces. Any work done due to such a force is actually conservative type work done, which is actually stored into the system as a potential energy. There are two types of forces we discussed so far like that. So the one is the spring force, which is store energy. Spring force, if you remember, F of S is equal negative K delta R. I'm going to put it delta R there because it can be X or Y. So if I calculate the work done due to spring force that we call the potential energy spring, which we end up by doing this integral, right? Integral of spring force times the displacement travel. So that I end up finally K over 2. I'm going to put R to the power 2, that R can be X or Y, okay? And that is actually the potential energy is stored inside the spring, which is due to work done of this spring force, which is a conservative force, right? Whatever the work done we do is stored inside the spring, it can release back, okay? And then similarly now, just we discussed the gravitational potential energy due to gravitational force, which is force times the gravity. Work done due to gravitational force, negative the work done, we call it the potential energy gravity, that we end up at the end of the calculation mgh, or force of gravity times ch. The another aspect of looking into this, particularly for this gravitational potential energy, now consider I have Earth here, and then this is the Earth center where the mass is concentrated. This is the Earth radius r. Then if I go above the Earth's surface, let's consider I pick a point right here. Let's consider that point is h distance above the Earth center. Now this every point which I pick, I can pick that this is h1 distance above the ground. We can pick another point right here, h2. We can pick maybe another point right here, h3. Each and every this point around the Earth has this gravitational potential energy already that we call the potential grid, right? We can't see that. We can see it only if I bring another mass into that. Now, let's say I bring the mass small m into that particular point, then that point has a gravitational potential energy of mgh1. If I bring another point right here, let's consider mass m2, then that object gonna have gravitational potential energy of m2 GH2, and then so on, which means around any mass particle, this potential energy grid actually can be visible. If I know a certain function for that, then we can actually visualize or simulate how the potential grid look like around the mass particle. Okay, so we will discuss those things at the end when we're talking about potential function. Now let's take a look this idea of conservative and unconservative type forces. Now the basic idea is conservative type forces means that anything we do into the system is stored inside the system, which means work done W is independent of the path. Okay, that's the important term, independent from the path, independent of path travel, which means what? Which means let's consider I have object right here. This is ground level. Ground level, we define the potential energy 0. Let's consider I have object here, mass m. I can bring that object from that point to the height h above the ground, right? So this is height h above the ground. This is point A. This is point B. I can go directly from A to B. That's one way to bring the object. Then I can say I calculate the work done from path AB due to gravitational potential energy. I get some number, right? Then I can bring the object in a different path. So let's bring the object initially from A to C, that is point C, then bring the object from C to B. So I first go A to C, then go to C to B. Then if I calculate the work done due to gravity from ACB path, this is path 1, this is path 2, both work done due to gravitational work done is actually same, because the reason gravity is always downward direction, so the work done at the end going to be the same, which means it's depending on two endpoints A and B, not how the object is actually traveled. Such work done is actually called the due to conservative type of forces. Okay, that's why force of gravity is actually conservative force. And then more mathematically, we can see if I bring the object back into the starting point, I'm going to get total work done is actually 0. Okay, and then we can easily define what is a non-conservative type forces. Non-conservative type forces mean work done is actually depend on the path travel, right? Depend on the path travel. What does that mean? Depend on the path travel means, let's consider I have an object. I bring that object on this. This is a like the horizontal plane. Okay, and then let's put the object right here, mass m. I'm gonna drag the object along this direction from point A to point B. Now, always frictional force gonna be against the path travel. If I calculate the work done due to frictional force, okay, frictional force from AB, then we compare that to another path. Let's bring the object from point A to point C against the friction, and then we'll bring that from C to B. Then I calculate the work done due to friction on that path, ACB path. These two are not equal, not the same, because friction does the work as you move the object. Friction force always against the motion. It does the work as you moving, which means two different paths, two different work done. Because of that, we call the friction is actually non-conservative type forces. Another way we can say the friction force can actually dissipate the energy from the system. it can dissipate. What does that mean? It can take off the energy from the system. It can convert mechanical energy into a thermal energy. Such activity cannot be done by the force of gravity, okay? It can only store energy. But the friction, on the other hand, get rid of energy. It can convert mechanical energy into a thermal energy, okay? Let's summarize this mechanical energy concept overall, right? Now we know this class, the physics one class overall, what we're talking about mechanical energy. Mechanical energy, now you guys familiar, basically can be categorized into two types. One is kinetic, when the object is moving. Other one is potential. Object doesn't move, but it's going to be relative to another point, right? Kinetic energy due to motion, that we know, which is 1/2 mass of the object, velocity to the power 2, right? The potential energy itself can be categorized into two types. One is due to gravity, other one is due to elastic property of the object. At this point, we only interested objects such as spring, right? So the gravitational potential energy we already figure out just now, which is mgh, and then that is relative to gravitational potential energy 0 point. 0 point is basically the ground level, okay? Gravitational potential energy 0 is the ground level. On the other hand, is spring potential energy. We calculated earlier chapter, half k, I'm going to put here r square, that r is the displacement change of the spring length, that again relative to 0 point. What is the 0 point for the spring, which is the spring relax point, okay? The spring relax point is the 0 potential energy point. Now let's take a look very quick, very quick small video for this small simulation for that. Okay, now this simulation I have a skater. I'm going to bring this skater. Now you can see this is the height 0 point, which means this skater doesn't have any potential energy, or it not moving, in total energy is 0, right? I'm going to move this skater up right here, which is, we'll say, roughly about like 4 meters above the ground. Then if I release this skater from here, right now I'm holding this skater. The skater above the ground has a potential energy. I'm going to release this skater, right? What will happen if I release this skater? As the skater goes down, potential energy becomes kinetic, and the kinetic energy becomes potential, and then we can see the energy conversion from one type to another, right? If you look at the graph above, you can clearly see that. So the kinetic is the green line, potential is the blue line. Those two lines are actually flipped each other depending on the position, right? Very bottom point, the red dot, has the maximum kinetic energy. Very top point has the maximum potential energy. Now, she can move, back and forth forever if there's no energy loss. But if I apply the friction, right now friction is 0 on the track, right? If I apply the friction, you can see now there's energy loss. You can slowly see the back and forth motion slowly reducing, and then eventually she's going to go back to 0 because there's energy loss as she moves in the system, okay? So that what we try to understand next, how we can now put this all the type of energy together into our conservation of energy format, which means earlier we wrote work done is equal delta E total, right? Total energy change should be work done. Now, work done due to conservative type forces already we included into gravity and into potential energy. Only work done now we are interested here, work done due to non-conservative forces. Most of the case in our problem gonna be just the frictional work done, okay? And then I can write in generally this one, work done due to non-conservative forces is equal total energy change kinetic, total energy change gravitational potential, total energy change spring potential, right? So we can simply say K final minus K initial plus UG final minus UG initial plus US final minus US initial, right? So that is when the non-conservative forces are visible. Let's consider non-conservative forces are not visible. Then WNC becomes 0. So in such case, we can say 0 is equal K final minus K initial plus UG final minus UG initial plus US final minus US initial. Then we can summarize this into total energy. Total energy at initial point is equal total energy at final point. Okay, energy has to be conserved somehow. So that's the idea. Okay. Let's bring this into more mathematical direction now. Since most of you guys in Calc 1 now know how to do the derivative, at least later you will learn how to do the integral and so on. We can take a look this more into more mathematical approach. Mathematically, how we can define these things. Okay. Now, we are talking about right now one-dimensional motions, right? One-dimensional system. So the conservative forces, mathematically we can define net work done along the closed path, okay? Integral along the closed path, net work done is actually zero, F dot dr. Now, since I'm working in one-dimensional case, then in this case, dr vector is actually just the dx, or it can be dy. Okay, the r vector can be just dx, x-axis motion, or maybe dy on y-axis motion, or dz in z-axis motion. This d mean infinitely small amount of change, right? So that's the idea, which means if I bring the object along the path, such as we did earlier, right? So let's consider I have a ground level here, UG 0 point. I have object here. Let's bring the object up. Now I'm moving against the gravity, and then let's bring it up to this point, maybe h distance above, point A to point B. Then we'll bring it back B to A, right? So if I do this motion, this is now cyclic motion, right? If I calculate the total work done gonna be integral f dot dy along A to B, right? This from A to B, and then plus integral B to A, again f dot dy. Then I can calculate this into total energy zero, right? This is gonna be just negative the mgh. This is gonna be positive the mgh. So that's going to be cancels out into zero. That's the idea. Okay, so we can do this calculation more mathematically or more conceptually like we did earlier. Now, the 1D case is fairly very simple. Okay, it did not really super, anything much interesting. But if you take a look the two-dimensional case, that is what we're really interested in. Okay, let's take a look the two-dimensional case. Now, in two-dimensional case, how I can understand the conservative force? That's a little bit tricky. We can't define that the way we did earlier. That's why this calculus is actually important. That's why the Newton actually invented the calculus to explain the Newtonian mechanics, because Newtonian mechanics you cannot apply otherwise. Without calculus, that actually has no meaning. So let's take a look now. If I have a two-dimensional force, such as a force like this one, has a two component. Okay, so this is like xy plane. So this is x-axis, this is y-axis. So as you go xy plane, at any given moment, I have a force with these two components, right? Let's consider I have a fx component, I had direction, fy component, j had direction. Now, if I move this object, let's consider mass m, point particle. I'm moving this object along some path on my xy plane. Then how I going to understand whether these forces are conservative or not? So to understand that, the basic idea is we take a look the work done. Now, this work done in terms of, we are talking about because this is a function, okay? This can be a complicated function, these fx's and fy's. So what we needed to take a look, the work done due to these two components at any given time, along really infinitely small distance travel. So if I consider a small distance travel along x, very, very tiny distance along x, dx, then I can figure out, or I can calculate what is the small work done along x-axis direction. Okay, that's going to be just basically fx dx fx dot dx, since both are in the same direction, this is going to be fx dx, right? I dot I, you can write it down more in detail. I dot I is 1. This is going to be basically fx dx, right? So that is the work, small work done on x-axis direction. If I move the object very, very tiny amount, right? So similarly, I can calculate a small work done along y-axis. That's going to be fy dy, right? So if that's going to be again fy magnitude dy magnitude, this is going to be j dot j is 1. This is going to be just fy dy. Now, if I calculate these two really, really tiny, infinitely small change due to these two forces, because this happening simultaneously, right? Two forces acting on the object simultaneously. So that's where this partial derivative actually come into a picture. In such motion, if I get these two are equal to each other, then we call such a force is actually conserved force, okay? Conservative type force, which means energy must be conserved acting such a force. So which means we can basically say now this fx dx should be equal to fy dy. I can convert this into a little bit more applicable method. What we're going to do, if I take the derivative d of fx over dy, small change I'm doing, okay? And then if I take the derivative of d of fy over d of x, these two should be equal to each other. That's the idea, okay? So that we call the exact differential. So if I can find it out, if I have a more complicated force function, which can be two-dimensional or three-dimensional, if I do a small change at any given moment, then I can figure out the net work done is the same for both motions, x and y, which I can do it very easily. I don't need to calculate that work done. I can do very easily by looking into this exact differential along x and y. Then such a force is actually we call conservative type forces. Let's take a look, simple example, right? Here I have a force written this way. So I just need to take a look if I want to understand if it is a conservative force. I'm going to take a look x component divide by dy. So if I do that, d over dy, we are interested only x component, right? A x square y. I had nothing to do with the with the differential at all. It's a direction, right? A is a constant. X is remaining constant when I do with respect to y, right? Differential. This is going to be basically dy over dy. That's the idea of partial derivative. When you do more than one function, more than one variable with respect to one type of variation, then the other variable, we keep it constant. That we call the partial derivative. That's what exactly we do in here. I don't write it as a partial derivative right now because we are not interested doing any partial derivative particularly, okay? Now this is equal ax squared, right? Let's calculate now d of x fy divided by dx. If I calculate that, d over dx, parentheses, ay square x. Now, in this case, if y is remaining constant, this will be dx over dx. This will become, say, y square. Now, clearly, I can say partial derivative or the derivation of fx over dy is not equal to derivative of y component over dx. This is actually non-conservative force. That's the idea, okay? We can identify whether the force is conservative or not by looking into that derivation. So we will do this example then. This is going to be then d of x component over dy. So x component over dy. So let's do that. D over dy, parentheses, ay is square x. Then the ax comes out, dy is square over dy. This is going to be 2x, 2xy, right? So that's it. Very simple. And then we'll do the y component over x with respect to x, d over dx, parentheses, ax is square y. then the AY comes out dx square over dx. So that's a power rule, right? This is going to be dxy again. Now, clearly, you can see it is exact derivatives are the same, which means d of fx divided by dy is same as the y component of x. If you cross multiply, then I can verify that the small work done is actually the same, right? So that's the idea, right? If I cross multiply d of fx dot dx, right? So that is same as the d of fy dot dy, right? So which means the work done along both direction at any given moment is same. Now this is a conservative type force, okay? So likewise, we can study various complicated function this way to identify whether the function is conservative or not, okay? And then there's another interesting application of this, particularly the calculus is actually potential function. Earlier I mentioned that very briefly right here. Potential is actually there around any mass particle. So what matters is actually how that potential is actually look like, right? So that how the potential look like around the mass particle is called the potential function, right? Let's take a look how the potential function can be applied in terms of more mathematical approach. All right, let's take a look at the potential function. What does potential function mean? So we know work done, we define as the negative the work done, we define as the potential, right, earlier. So the potential, in general, we can say negative the work done, which means the potential, we can define negative the integral f dot dr. So I'm gonna use dr because dr can be x or y or z or all three at the same time, right? Now you can clearly see the potential is actually integral of the dot product of the force, right? So it's the small work done. If I integrating means I adding total work done, right? So now, which means if I reverse the process, right? So if I do the integral, then I can find the potential. I can reverse the process, right? If I reverse in the process means I can take the d of u over dr, right? So if I do d of u over dr, and if I add the negative sign here, I can figure out the force. So I'm going to put the unit vector r there to represent the direction. Now this r can be anything, which means I can do this at any given time, x-axis direction, negative du over dx I had, or I can do this y-axis direction, negative du over dy, j hat, or can do this z-axis direction, negative du over dc k hat, right? All of these together, I can rewrite this thematically very easily into a more than a system. Let's consider I have a 3D system, right? If I have a 3D case, then such case potential can be function of x, y, and z. Remember, the potential is a scalar, okay? But if I take that scalar, potential is a scalar function. If I take the scalar and then do the derivative, then I have to end up with the vector, right? So which means I can rewrite this force on x, y, z direction should be equal negative du over dx. I had negative du over dy j hat negative du over dz k hat. This we generally write by using what we generally call the del operator, okay? So this is now partial derivative. Partial derivative means function can change at any given point all three direction, but we are treating at any given point when I do du over dx, we treating other two variables I stay constant, right? When I do, that's why we're writing this partial, right? When I do partial over partial x, then I treating y and z are constant, right? Similarly, when I do partial over partial y, we're gonna do x and z remaining constant, and then so on, which means del operator is actually look like this. Del operator mean which is a vector partial over partial x I hat plus partial over partial y j hat plus partial over partial c k hat. This partial mean it's same as d over dx, but we're writing it partial because now when I do du over dx, which means that the other two is actually stay constant really, okay? But in this case we are using partial the base, but it means basically other two sides also can change, but it treating at any given moment as remaining constant, right? So which means I can write the force function now. It can be a three-dimensional force function which is equal negative the del operator times the potential function xyz, which means our force can be negative partial over partial xu I had negative partial over partial yu, j had negative partial over partial z, k hat. Okay, so that's the idea. So it is fairly very simple mathematical model, but you needed to know or learn how to use this concept carefully to work with such kind of situation. Let's take a look with a simple example, which is not our primary focus in this class, the learning calculus or anything. Okay, but let's take a look how to do that for one simple example. Let's consider I have a function, potential function, which is a one-dimensional case, is equal to 2.5 x to the power cube plus 5.1 x to the power 2 plus 8.3 x, which means x, this is a x direction situation, one-dimensional situation, but you can see potential is like very complicated, right? So it's not just a linear function, it is a very complicated function, right? Third order polynomial. Now in such case, if I want to figure out how the force look like on x-axis, I can do del operator times the ux. Since it is one dimensional, we don't need the del operator. I can just write d over dx, I hat direction, right? So I have negative d over dx. I have here 2.5 x to the power cube, and then I have negative d over dx 5.1 x to the power 2. Then I have negative d over dx 8.3 times cx. I'm going to put the I hat outside. Okay. Then we'll do the this operation, which is a power operation, right? 2.5 comes out. This is going to be x to the power 2 over dx. That will becomes 3x squared. Okay. Then I have minus 5.1 comes out, 2x power rule minus 8.3 parentheses I had outside. That's it. Fairly very simple calculation, right? So that is the force function at that particular case, right? Now the force function, again, you can see a complicated function, right? Which means along the x, different places can have different numbers. Now, if I want to find the value of force at any given moment, all I needed to do, substitute that number for x. Let's consider x equal 1.5 meter location we interested to see what is the exact value of the force. Then all I needed to do, substitute that number, negative 2.5 multiplied by 3 multiplied by 1.5 to the power 2, right? Then minus 5.1 times 2 times 1.5 minus 8.3, and then I hat unit should be Newton, right? If you simplify it, you will get a number here, direction I had unit Newton. That is the exact force value at that particular moment. That last few slides are actually for interest. It is nothing to do with our quiz or anything next week. Our quiz is basically based on this particular concept. Okay, so you needed to know how to apply particularly this concept. Work done principle in more general terms. That's what our next quiz gonna be based on. That last 3 slides, which is more how the calculus is actually can be used to explain more mathematically this concept, is actually for general interest. Okay, so I'm going to stop from there. So we will continue next week. All right.